Hey, good afternoon. What I'm going to talk today is about solar flares. So this is one issue in science which is already addressed by a number of experiments, but I hope to convince you that with the addition of a small payload on a small satellite we can do much more. So in short, I will just remind you what solar flares are and tell you about the current observation of them by the RESI satellite and the new observation which we will perform with sticks, and mention also what are the problems which with a single instrument we cannot solve. Okay? And then I'm going to talk about a new small detector which is called MiSoIFA, so very musical sounding, and this is going to help in understanding those problems. And I will also mention the possibility that we fly this instrument on a Swiss small satellite, and this is in conjunction with an EUV instrument or a standalone. So, solar flares and coronal mass ejections are very bright phenomena which happen very often in the sun. They have a very wide range in magnitude, so typically you have soft solar flares happening very often, and strong ones happening more rarely. Okay? But you get an incredibly wide range of them. And many of them are accompanied by a release of charged particles, and those particles travel along some highway driven by the magnetic field of the sun and reach the Earth, where they can cause beautiful aurora or maybe troubles like blackouts and so on. And so solar flares are important phenomena for the dynamics of the solar system, and are also very interesting from a physical point of view, because there we get a huge energy release in periods, and this is basically magnetic energy in the solar corona, which gets converted in a very rapid way into kinetic energy, and the details of that are not well understood. But we know that they are detectable as very powerful X-ray sources, and this means that there are electrons which get accelerated. Okay? So this is an example of spectrum on the left, measured by RESI. This is a satellite which is operating since 2002. And you have typically two components. The red one is a thermal component, and then you have a non-thermal tail, the blue one, which is typically falling down like a power law or a combination of power laws. And you will notice that the log-log scale. So this flux is huge, but it is dominated by low energy electrons. And we can also try to make images. This is done on the right. So the grayscale image is a UV image by RESI satellite, and then you have two distributions. One is low energy, which is this loop, giving you a visualization of the loop connecting the two foot points, the blue ones, the blue regions, which emit very strongly and very high energy photons. This kind of image is done not with the optics, but with the Moret technique. We'll mention this a bit later. And one limitation is that at the same energy, if you have two sources, one which is fainter than the other by a factor of 10, say, which is not very difficult in astrophysics, then the second source is invisible. So this is a main limitation. And the other thing is that we always have this single point of view, so it is very hard to know what is, for example, the height of the foot points. And as the particle density and magnetic field configuration change quite drastically when moving radially out of the sun, it is very important to know that. So we could benefit from sort of stereo observation, so two points of view which are different and looking at the same phenomenon. Now, at present, RESI is working very, very well, and it makes beautiful solar flare data. And we are developing sticks in Europe. Sticks is one of the 10 instruments of the M-class ESA mission solar orbiter, and it is going to be launched in a few years and will operate mainly in the next solar massive period. So how RESI makes images? It has grids. Okay, look at my fingers because I cannot do that better now. They cast shadow. Okay, and the way the shadow changes with time is connected to the rotation of the satellite. And this brings information about the rotation itself, about the time variation in the source, but also about the position and geometry of the source. It is a bit complicated, but you have examples here on the left panel which you are not required to understand fully. What I mean is that RES is rotating, and by performing complicated mathematics, we can get Fourier components out of these oscillations and then build an image from them. Now, solar orbiter will not rotate because there are instruments which don't want to. So the X-ray imager will be based again on Moray effect, but we tilt the grids and make a shadow which has a characteristic period, as you can find on the right plot. And the phase of this pattern depends on the source position, the amplitude of the pattern, so the contrast, if you like, between white and black bands, depends on the source size. Again, we get Fourier components, we get a total of 30 components in 10 different angular scales, and then we build the image mathematically. Now, why solar flares interesting from a scientific point of view? We have Bremsstrahlung radiation, which is detected as X-rays from the electrons, and we would like to know how the electrons get accelerated. We know that they somewhat lose a lot of energy in the full points, but we believe that they are accelerated higher in the corona. Okay? The problem is that we cannot observe the coronal emission together with the full points at the same energy because the coronal emission is at least 100 times fainter. And with this technique, you don't have this dynamic range. And another problem is that if we think about the acceleration of electrons which follow some bent trajectory and hit the chromosphere in 2 points, it is very intuitive to think that they are beamed. Okay? Unfortunately, all measurements that have tried to quantify the asymmetry or the anisotropy of those electrons are basically compatible with the anisotropic distribution. So it is either the problem with the measurements, which we believe is the case, or we lack understanding, okay? Which hopefully it is not the case, but would be exciting. So let's say that we want to image the coronal source together with the full points. Do we have a way of doing that? Yes, we do. We could use grazing incident optics. There are no lenses for X-rays. But you can build these kind of optics. The problem is that they are heavy. They need very precise alignment with the focal plane detectors, which are 10 meters away. So these kind of satellites are not very cheap and are not very simple to build. And there are proposals about them, and few of them also exist, but it is not easy to get them to look at the sun. For example, we have a prototype, Foxy, which flown on a rocket, and just for 6 minutes it was lucky to see a solar flare. It was a great success. Okay? But even if we could get these grazing incident optics, that would be inferior to the Moray for 2 points of view. From the angular resolution, the Moray gives you better angular resolution, and for energy range. You can only get reflected photons about below a few tens of keV, but if you want to go higher in energy, you cannot get grazing incident optics working. And the other thing which we would like to do is to estimate the directivity of the emission. So we would like to know whether the electrons are really beamed or not, which means whether the X-rays have the same intensity everywhere or just very different intensity along 2 directions. So what we do is that we are developing a small satellite called MiSoIFA, which is supposed to complement STIX. And this is a possible layout of the satellite, so don't wait, this is not very important, because we are still working on the configuration. And what are the goals of MiSoIFA, the micro solar flare apparatus? The first goal is that, together with STIX, we want to make simultaneous imaging or observation, better, of coronal and full point sources. And we can do that if, for example, a flare has the 4 full points occulted by the solar limb, so that the coronal source is visible by one detector and the full points are visible by the other, then we can do this measurement. But we need to have 2 detectors which have the very same energy resolution. Because there were attempts so far to make this kind of combination of data using different satellites. But the problem is that maybe you remember that the spectrum is falling down very quickly. So if you make even a small error in the energy determination, you are completely offset in the number of photons. Okay? So you really need two detectors which have the very same energy resolution so that you can sort of make the ratio the histograms in one coarse way. Then the second goal is to measure the directivity of the emission, and again we need to have the very same energy resolution. And the third goal is just to extend the sample of solar flare data, even if there is no other experiment working in that moment, because STIX will have only science windows for a few weeks, every number of weeks, and then it could be on the other side of the sun, because the solar orbiter is orbiting around the sun, not around the Earth, and so on. So this detector MiSoIFA is very compact, and we can also fly it on a CubeSat. Of course, not in a single cube, minimum would be 3 units, but we are aiming at 6 units. And it has two possible configurations. One is a pure spectrometer, no optics at all, no imaging, and the other is with imaging. Now, imaging is, I already mentioned that we need the very same energy response as STIX, so for this reason we use the same detectors. You will get more details about them by the talk by Henri Trieu, which is later this afternoon, so I don't spend time on them. About the imaging. Imaging is possible in a nanosat only if you have grids which are very small in period. So you need to go to a few microns period, and this is challenging. So we are investing on development of the grids, but it is not granted that we are successful in doing that. Let me skip that, and let me mention that we have the possibility of installing MiSoIFA on a Swiss satellite, which has two possible configurations, shown here very, very shortly. One has X-ray plus UV, and the other is only X-rays. In case of the Swiss satellite, we need to develop the platform, and there is interest by the Swiss Space Center, by the EPFL, and by Flight Space into making a common research and design and development. That would be a 6 units, and we feel that this is large enough for good science, but small enough to be cheap. In case we work with the EUV instrument, which is developed by the Institute Davos, in Davos, which keeps the World Radiation Center and the World Radiometric Reference for the total solar irradiance, they would provide two complementary ways of looking at the sun, because in the EUV you are interested in the quiet sun period, you want to know the power emitted by the sun, and then maybe you check what are the climate effects of that. And when there are solar flares, typically these data get discarded, but we can also use them. For example, in this plot you see the black curve is the high energy flux of photons from resin, and you see that this is very sharp. Okay? And then you can see that the lower energy, for example, the red and blue, which are red is soft X-rays and blue is UV, you have an increase which is lower. The interpretation is that the high energy electrons are heating the system. So they transfer energy to a plasma, and this plasma heats up, and so it starts emitting also at lower energies. Okay, this is an example. I just want to mention that this is a collaboration by our institute in Windisch, CA Saclay, providing the detectors. We have also at PSI in Villingen and Microworks in Karlsruhe, who are working on the grids. Of course, there is the PMOD and WRC Institute in Davos, and Lausanne and Flight Space are working on the platform. The summary is that we propose to build a small detector which is based on the same technique that we use for STIX, to have complementary measurements which will open up scientific perspectives which are impossible for any alone instrument. Even though this instrument is very expensive, if it is by itself, it cannot answer those questions. And we have the option of installing it on a compact satellite developed in Switzerland, which we hope is successful. And for this, the likely configuration would be the X-ray spectrometer plus the EUV. Thank you.
Thank you, Leo. I think we have time for one question.
What is the energy range of the X-rays you want to do the imaging? I didn't catch the number, the range.
Yeah, I didn't take the number here, sorry. The energy range, the interesting energy range is in between the transition between the thermal and non-thermal spectra. And this transition is different flare by flare. So we will work between 5 keV and at least 50. Ideally, it would be 500 keV. This transition usually happens between 10-15 and 20-25 keV. So we want to be able to fit the two spectra. The thermal spectrum on one side, in which you see the spikes due to the excitation of ion lines, and the non-thermal one. So the total range will be 5 to, let's say, 100 keV. The resolution is better than 1 keV in this range.
Yeah, I understand the energy resolution, but to make imaging with grazing incidence in such a small volume with these high energies, it will be very challenging.
Yeah, I will not use grazing incidence. I said that grazing incidence will not work within our course. We will use Moray. With the Moray, you can get up to MBD range.
Thank you, Diego. Very far-reaching. Appreciate that.
Thank you.
Please now.